everyone, welcome to this design practice 2 module 18. We were discussing about photolithography, and in context of that I would like to do some more analysis related to the process. So, as we already found out that this process of lithography is categorized into 3 different ways of doing printing. So, one is contact, another is proximity, and the third one is projection printing. In the first 2 techniques, namely the contact and the proximity printing, the mask is brought close to the substrate. In one case there is small gap between, particularly the proximity case, between the wafer and the mask, and the contact printing sort of lets the mask even touch the photoresist layer, which is actually detrimental sometimes for the resist layer. So, when we look at particularly the contact printing method or even the proximity printing method, the resolution of the process B would typically depend on the wavelength of the illumination source, as well as the distance of the source from the particular layer of resist which needs to be exposed to. So, if the resist distance is changed, the resolution will definitely change. For example, if S goes up in this particular expression, or the distance between the mask and the resist layer goes up, there is a change of the resolution B. So, the B will also go up, meaning thereby that it is lower resolution. B is typically the distance between 2 different objects spaced and get visible independently. I think we just need to reiterate what resolution really means. So, let us say there are 2 points in space, and so the B goes up, meaning thereby that let us say if the distance is more, the ability to resolve between these 2 points, this is B, okay. The distance between 2 points which still can be visualized by an eyepiece situated at some distance from the 2 points as independent. So, as this B reduces, the points become merged into one another and they may not be able to get independently visualized. So, here the whole purpose behind the experiment is to just make the B as small as possible, considering a distance S from the eyepiece to the particular substrate, or let us say in this case the resist layer. So, obviously, when we are trying to pattern within microchannels, for example, in one particular instance in a particular flat silicon wafer, there has been a channel which has been carved because by etching techniques, okay, something like this. There is a channel, and this is the remaining part of the wafer. So, we want to pattern somewhere in this particular surface which is hashed on the inside surface of the channel, and obviously the placement of mask in this particular case would happen in a manner so that the mask is present over the surface, and the windows which would let the light go in are present at a certain height h from the channel surface. So, in such kind of cases, it is obvious the resolution would depend also on this distance h as well as the wavelength of light that one is using, S being the distance between the mask and the resist layer. So, supposing the resist layer were kept here and the mask layer is this particular layer which I show through this vertical line hatching. So, the h distance between the resist layer and the mask layer is basically the height of the channel or the depth of the channel in this particular case. So, let us say we have now a resist layer at the bottom of a 5 micron deep channel and another one at a 20 micron deep channel, and we want to pattern and we want to find out if the resolution is going to change, is it going to be more or less. So, if B is more, the process is less resolved, because obviously B lesser and being able to independently resolve means the resolution of the process is higher. That is very clear from the terminology related to resolution. So, in this particular case, we have 2 different resolutions, let us say B1 and B2. One is at the behest of a 400 nanometer beam. Let us say we resolve everything in terms of microns. So, we have 1.5 times of 400 10 to the power of 3 minus 3 microns times of S, which is 5 microns in one case, whole to the power half, and the other case, once the distance of the channel becomes 20 microns, this is into 20 to the power of half. So, if we compare both the resolutions, obviously the resolution is better in the first case. B has a lower value in comparison to that of the second case, and the resolution would be simply reduced to 1/2, as you can see here, B1 by B2. So, when we compute B1 by B2 in this particular case, we have 1/4 to the power of half, which comes out, which is half. So, basically in the case of B2, the resolution is simply reduced to 50%. Okay. So, the minimum feature size that can be accommodated at a channel depth of 20 microns is going to be exactly twice the feature size that can be accommodated at the channel depth of 5 microns. So, these issues need to be kept into mind while developing mask designs, particularly in the MEMS application. And let us move ahead now into actually how you do lithography. So, lithography can start from a cleaning step, where a substrate, particularly a silicon substrate, is taken and cleaned through various cleaning protocols. The idea is to get off all the organics and other contamination which is there on the surface. After the substrate cleaning step, you take photoresist and spin coat this on the wafer, creating a small thin layer of the photoresist film on the wafer. You pre-bake or soft bake the film and remove all moisture content from the particular field film, and then you expose the pre-baked film to a certain wavelength of light using a mask. This is a well defined mask, which is in the beam path here. This is the beam path with the beam guidance, which is given by the optical alignment engineering of the photolithography system. After the exposure, you need to heat catalyze the bonding mechanism, which would happen. Let us say if we are talking about negative tone, there is going to be cross bonding, and so the cross bonding gets affirmed more because of more post exposure bake, and then finally you develop what you have done on the film surface. So, supposing it is a negative tone resist, so what the areas exposed would going to remain away, the remaining are going to be etched off because of this development process, and then you post expose bake it, because post develop bake it, because you want to get rid of all the liquid from the surface, particularly the developer solution which is left over after all the resist is successfully removed. Isopropanol is typically used for finding out if there is a residual resist which is unexposed left on the surface. It becomes whitish or cloudy, and so once you have no cloudiness by spraying isopropanol, you are able to figure out whether the resist is all removed. And so you do post exposure bake or post development bake, which also affirms the cross developed or cross bonded areas which stay back on the wafer surface. And then you etch out the thin film, which is related to whatever you are using this for a mask. For example, lithography is typically carried out because either you want to use it for a lift off end process, or you want to use this for a etching process, and we must keep this in mind that resists are normally always used as sacrificial material, unless you want to develop something with the resist like a micro cantilever or something like that. So, you etch the thin films and then strip out the photoresist, so that you are left with the etch pits on the thin film that you wanted to etch for. So, a resist would act as a etch stop layer in those situations. So, this is all about how photolithography is carried out in the laboratory. If you look at the various aspects of the lithography process, it starts with a spin coating of resist, because you want to spread the resist. So, there is typically 3 different components in a resist. One is a photoacid generator, another is an epoxy resin which kind of cross bonds on exposure because of the furnishing of photoions, and then there is carrier solvent. So, the solvent is typically used for spreading the photoresist uniformly like a film on a surface. This is a spin coater to do this job. You drop the photoresist on the center and it spreads out as the wafer, the silicon wafer shown by the green piece right here, rotates at a certain RPM. Then you do soft baking in a gravity fed convection oven like this. You do a alignment exposure step. You can see the mask here in the lithography system. So, the mask attaches into a frame right here in this area, and the wafer is kept down underneath. So, this is the wafer chuck in fact which goes inside and aligns the wafer with respect to the mask. This is the exposure box, the counter which also counts time as well as sets up the intensity level. There are many other visualizing tools, for example, a CCD, a screen which is here. So, this is for visualizing particularly the backside alignment issues using infrared camera, etc. There is also a objective and a set of eyepiece here, and there is a microscope in place to visualize whether alignment is being carefully done. Okay. So, and then there are various other components like a light source. There is a shutter which would be operating on the light source to expose or unexpose whenever whatever times are set in, so on and so forth. So, the process happens with first the mask loading. You can see mask being loaded, the wafer loading, okay, and then the process alignment, and then the exposure. So, these are the different steps carried out on lithography. And then you have, after the lithography has happened, a timed development where a solution is used, a wafer which is already exposed to light is dipped in, and material is taken off, so that you have the sacrificial resist patterned on the wafer, and you use again a etching solution to etch off the film underneath the resist, so that you could make vias or crevices or craters into that particular film which you are etching through this process, for which the resist is actually a etch stop. So, this is how different steps of lithography are executed. Typically in high production systems, the spin coater and the nozzles are eliminated, and so there is spraying system which will do the job of spraying the resist at a high pressure and ensure that there is uniformity in thickness. And then there are large machines called steppers which are used sometimes for the purpose of high throughput lithography. So, these are how the process is carried out, and these are all projection lithography based systems. Process is carried out in the industry in a very high yield through the following things. So, if you looked at the basics of what really is changing in the resist, what is the reason why the resist changes properties? Primarily SU8 has an epoxy structure. It is a carbon oxygen carbon ring as shown here, and then if we looked at what all components are there, you have a epoxy resin as the base matrix which would be cross bonding whenever there is a exposure to light. There is also a carrier solvent which evaporates in the pre-exposure bake step which is executed, and then there is a photoacid generator, something like what you can look at here, which is actually a Lewis acid and generates protons. And typically when such photoacid generators come in contact with radiation of a fixed wavelength, they are going to generate protons which are going to then start affecting these epoxy rings. For example, this proton right here has started opening the epoxy ring, and two such rings simultaneously opened would cross bond like you are being shown here. So, this is like the cross linking mechanism of the resist which goes on happening, okay. And so, you can probably have the proton retreated back, part of the same molecule, the photoacid generator molecule, but what it has essentially done is to gone into the system and opened up rings so that they can cross link, and such cross linking is important for the process of lithography. So, it is a sort of a cross bonding polymerization kind of reaction where multiple organic molecules come together and cross linking develops between them, so that they can be enabled to stay on the surface without the developer solution being able to etch them away. And so, partially the structures which are on the surface in a negative tone resist are the ones which are cross linked in this manner. So, there is a lot of associated methodology which is very carefully drafted. For example, the way that light source is able to expose the photoacid generator and the way that diffusion processes for the protons to start going out from the photoacid generator and affect the epoxy rings are mechanically limited would really determine the extent of finish that would come onto the structures that are enabled. For example, this shows schematics, or this shows microscopic images for structures developed. These are like microchannel structure developed for different time instances of exposure. So, in one case we have underexposed, actually both of these cases we have underexposed the surface, and so you can see that probably the proton diffusion is not proper, relating to a lot of wavy edges, under dimensions, because you are not allowing enough time for the exposure and the protonation to happen. And then once it hits the right time, it automatically changes the surface roughness of the channel. So, the smoothest channels here, and this is a plot of average roughness with time of exposure. And so, if the time again increases to few more seconds, then it starts over diffusing, and then it starts changing the dimensions to slightly oversize, which is also something which should not be allowed. Okay. So, it is very carefully planned and drafted if you want to have good patterning process on the system, and every patterning process has to be developed ab initio by looking at the various resist parameters and then trying to balance out the times, the thicknesses, the spin speeds, the heating times, the development times, so on and so forth. So, typically with this kind of resist, this is sort of a step which shows how resist acts as a sacrificial material. This is let us say a etched top film which you want to expose. So, you have used resist as a sacrificial material and selectively taken off with etchants the hatched area, so that it can open windows for the base material which can be further etched. Okay. So, the resist is typically removed, and then these are used, the sacrificial material here is used as a way of etching out the main material. Okay. And then you can even remove the sacrificial layer off. So, that is how bulk micro machining is typically performed with resists and with patterning on surfaces. So, you could do a lot of processes through such lithographic techniques. This right here shows how you can use exposure step followed by the selective etching of the blue film, okay, the blue colored surface, okay, which is outlaid on the substrate surface. It also shows how you can remove the photoresist. So, this shows how a layer of this blue region on the substrate is being selectively etched through lithography. So, this is a resist, it is a Shipley positive tone resist which gets debonded on exposure to light. There is a mask which has been kept. So, the resist is patterned here, opening vias, and the gray layer which is underneath the blue photoresist layer gets etched off because of the opening of the windows in these two regions, and the resist acts as a sacrificial material, thus exposing the green area now, which is just underneath the gray area. And then after doing this, the photoresist is removed and another layer is coated where you can actually carry out metal deposition. So, this is again lithographed, a pattern like an interconnect is created, vaporization of metal is made on the top surface, and once the metal comes and sits on the surface, the green area, you can take off the resist layer so that you have interconnects on the final device as is mentioned here. So, patterning by etching, deposition and lift off all at one go is in fact represented in this particular slide, which gives you an idea of what can be done with interconnects, with etching features and structures, producing mechanical and electrical features, and a variety of things as per plan on surfaces of materials like silicon. So, I talked about various other MEMS processes. I want to in fact finish up this area today, so that we can start doing the sensor design and actuator design after that. So, there are additive techniques like chemical vapor deposition, where you can create some kind of chemical reaction, the byproduct of which is a solid film which can get deposited on the top of again silicon. So, you can carry out, so this is called chemical vapor deposition. CVD can be carried out under different pressure conditions. For example, there can be the APCVD, the LPCVD and the PECVD, the plasma enhanced chemical vapor deposition. And the APCVD, LPCVD involve typically elevated temperatures ranging from 500 to 800 degrees Celsius. These temperatures are too high for metals, particularly with low eutectic point, and you can use materials like gold which has about 380 degrees Celsius eutectic point, and aluminum which is 577 degrees Celsius eutectic point to some extent to make deposition possible. Okay. PCVD is basically plasma enhanced, so there is going to be a bunch of ions and electrons, and you can have a drive energy so that the films become stable. Okay. So basically the PCVD processes have a part of their energy in the plasma state, and so lower substrate temperature is accommodated in these kind of cases where the films are still stable at a low temperature. In this particular case, in APCVD or LPCVD case, because of the fact that there is no such momentum transfer, it is the temperature which tries to build up a kinetic energy on the surface so that there can be a diffuse layer which acts as an adhesion promoter for the metal that is deposited on the top of the silicon. Okay, so this is one additive manufacturing technique responsible for doing surface micromachining. There is another very interesting thermal oxidation process where you are using thermal energy to excite the crystals on the top of silicon wafer and then passing oxygen molecules close by, whether they are in dry or wet state. Wet state, the reaction rates are very high, and typically the silicon wafer, for creating a condition where it can start entrapping the oxygen, needs to be heated to 800 to 1200 degrees Celsius in a quartz tube, something like this. The wafers can be stacked inside this tube, and the furnace can be set up at a high temperature, and the oxygen flow at dry condition or passing through a bubble trap so that it has water vapor and oxygen can be passed close into the through the particular tube and through surrounding the particular wafer at a higher temperature, so that there is diffusion of molecular oxygen into the substrates. So one has to realize something here, that when we talk about oxide layers, the oxide layer kind of gets built on the surface at the behest of the silicon. So you have plain silicon which is now heated up and oxygen diffused into the silicon. So there is going to be some bulging and deformation of the film, and let us see how. So we have a case here where we want to find out what is the thickness consumed of silicon for certain silicon dioxide film to grow on the surface. Some parameters are given, for example, the density of silicon, that of silicon dioxide in terms of kg per unit volume is mentioned. Molecular masses are also mentioned for silicon and oxygen as kg per kilomoles, and we want to find out what is the consumed silicon thickness for a film of size D or thickness D formulated because of wet or dry oxidation process. So if we look at the stoichiometry of let us say the dry process, we know that at the behest of 1 kilomole of silicon we are going to get exactly 1 kilomole of silicon dioxide. Okay. So exactly there is a 1:1 molar ratio. So if we treat this case in a manner that, let us say, the exposure of the surface, this is a crystal lattice and you have cubic crystals, and I am actually showing you a side view of such a lattice, and so there are oxygen molecules which are there, and let us say the crystal lattice is also oscillating because of thermal energy, because of heating and all, and the oxygen somehow gets trapped into this lattice and starts diffusing through the structure. So there is going to be definitely the use of silicon to formulate the silicon dioxide, and let us assume that the area here of the silicon and silicon dioxide are similar, that is A. And so if we wanted to look at the volume ratio, that means the volume of silicon dioxide to the volume of silicon, it is really about how much is the size of the silicon dioxide vis-a-vis what is the size of the silicon in terms of thickness which is consumed. Okay. So we assume that the silicon and the silicon dioxide before and after the oxidation are having identical nature. So I think in the interest of time we will try to close on this module, but after this understanding we will try to solve in the next lecture what is going to be the ratio of the two different thicknesses in this particular case, and then this close over with 1 or 2 more illustrations of MEMS processes and start with the sensor design. So as of now, thank you very much from my side.